I want to take a look at the tangent and cotangent parent functions. In my opinion, the two hardest trig functions to understand graphically, at least initially. Once you get experience, it's not too bad. But if I want to graph y equals the tangent of x, I have to consider in my angles in my coordinate plane or my reference triangles that tangent is going to be the opposite over the hypotenuse. So it's a ratio of, or sorry, not opposite over hypotenuse, opposite over adjacent. Okay, sorry about that. Opposite over adjacent. So it's a ratio of two sides, and it doesn't involve the hypotenuse. Lots of times when we deal with the hypotenuse, we can assume that it has a length of 1. So hypotenuse ratios aren't too bad to calculate. But opposite divided by adjacent can be a little more difficult. You can also think of the opposite side as the vertical side of your reference triangle and the adjacent side of your reference triangle to be the horizontal side. That can be helpful. So let's take a look at the coordinate plane here. And the idea is we're taking the tangent of x. So x is the angle that we're talking about in this coordinate plane representation. So if we start here at 0, the angle 0, the tangent of 0 is the vertical piece, which is 0 in this case, divided by the horizontal piece, which is, again, if we're assuming a radius of 1 or a hypotenuse of 1, that would be 0 divided by a horizontal piece of positive 1, which is 0. Okay? So here, if x is 0, or the angle is 0, the tangent of that, tangent of x, is 0. Okay? So if I were to graph that on a coordinate plane when I'm wanting to graph the relationship between y and x given by this equation, when x is 0, y is 0. The tangent is also 0. That's what this means. Then if I look at maybe up here at pi over 4, let's say x or our angle is pi over 4. I could label that over here on my graph as well. X is pi over 4. The tangent of pi over 4, well, since it's 45, 45, 90, my opposite, my vertical side, and my adjacent horizontal side are equal. They're both square root of 2 over 2. Dividing those out, I get a y value of 1. So the tangent of pi over 4 is 1. Now if we come up here to pi over 2, where the angle is pi over 2, the tangent of pi over 2 is vertical, which is 1, divided by horizontal, which is 0. That's undefined. So what that tells us at pi over 2 on my graph, I get an asymptote for the tangent function. And I'm sorry, I forgot to plot that when x is pi over 4, tangent is 1, so I need to plot that point. Okay, there we go. And so in general, what happens is I'm rotating from 0 up to this. My vertical side is getting closer to 1, and my horizontal side is getting closer to 0. And so if you look at the ratio of, if you take an angle that's like right here, the vertical piece is getting close to 1, but this horizontal piece is getting really tiny. And you can imagine that as you get closer and closer to the y-axis, the horizontal piece is going to get extremely tiny, like 0.000001. And when you divide by numbers like that, you get a huge ratio, a huge opposite over adjacent. And so whenever my angle is very close to pi over 2 on this side, my ratio gets really large. So what that means over here is as I get close to pi over 2 from pi over 4, my ratio, my tangent value gets huge. And so that tells us that as I move to the right, I'm increasing kind of slowly. But it picks up, and as I get close to pi over 2, it starts to increase really rapidly and goes up very quickly as I get close to that asymptote, and looks something like that. Okay? So that corresponds to the yellow rotation of the angles over here. So let's continue now. What happens when I hop over pi over 2? Well, same idea, right? My vertical side's really close to 1. My horizontal side is really tiny. Except this is negative now and this is positive. So when I take a ratio of something that's approximately equal to 1 divided by a really tiny negative number, such as positive 1 divided by negative 0.000001, that ratio is really big again, but it's a negative ratio. Okay? So whenever I cross over pi over 2, my graph actually is going to be pointing down near this asymptote on the other side because I get a really big negative number. Okay? But let's go on to see some particular values, such as this angle over here at 3 pi over 4. If x is 3 pi over 4, then the tangent of that equals, well, that's a 45, 45, 90. The vertical square root of 2 over 2. The horizontal is negative square root of 2 over 2. So tangent equals negative 1. So when I'm at 3 pi over 4, my y value of my tangent function is negative 1 instead of positive 1 like it was over here. And then when I rotate all the way down here to the angle of x equals pi, tangent of pi equals vertical, which is 0, divided by horizontal, which is negative 1, and 0 divided by negative 1 is 0. So when I reach pi, I'm back to 0. So what happens is this portion of the graph behaves much like this yellow portion. Let's move my negative 1 a little closer so it kind of matches up with how far apart my 1 is on the top. And then that means I need to move this point to right here. What happens is my graph, as I'm moving away from pi back towards pi over 2, again, it starts increasing in the negative direction very rapidly. See if I can draw this a little bit better. And I get this sort of behavior. So I approach my asymptote again, but in the downward direction. So that's what happens if I were to rotate this way, from pi back up to pi over 2. You start out at 0, your tangent value starts out at 0, but it gets big, 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 big forever as my horizontal side gets close to 0. And they're negative values because I'm in the second quadrant. And if I were to continue, what's interesting is if I were to continue, then what happens is I would actually repeat this yellow piece. So I can stop because now I have one complete cycle. One cycle. So for the tangent function, my angle only has to rotate through pi radians instead of 2 pi radians like sine, cosine, secant, and cosecant. You only have to rotate through basically half of the rotation of the plane to reach every possible y value on this graph. Okay, so this is one complete cycle of the tangent function. Now let's go look at the cotangent function. And the good news is we don't have to do the same analysis because cotangent is the reciprocal of tangent. So what we'll do is we'll graph y equals tangent of x from 0 to pi, and we can look at the reciprocals to graph the cotangent. So tangent starts and ends at 0, has an asymptote in the middle, goes up first, goes down second, okay? So tangent, if I graph this in red, here's 0, here's pi. It starts at 0, ends at 0, halfway between has an asymptote, and then halfway between 0 and the asymptote, it hits its value of positive 1. Halfway between the asymptote and pi, it hits the value of negative 1. This is our tangent function we just graphed, right? Halfway between. And then it approaches the asymptote as it moves this way, and it approaches the asymptote downward as we move this way. So that's one complete cycle. Now let's look at the reciprocals of this to graph the cotangent function. So we'll graph cotangent in blue. Here, tangent outputs 0, so cotangent is going to output the reciprocal of 0, which is undefined. That means the cotangent function is going to have an asymptote to start, and it will also have an asymptote to end, right? Because it's one complete cycle, or again, here tangent is 0, so cotangent is undefined. Now, whenever tangent equals 1, cotangent is the reciprocal of 1. The reciprocal of 1 is 1, so that the two graphs actually share that point. And similarly, the reciprocal of negative 1 is negative 1, so the two graphs share that point. Now the question is, what happens here at the asymptote for tangent? The reason this was an asymptote was because we were dividing by 0, if you remember, right? If we go back up, we were trying to divide by 0 here, 1 divided by 0 at pi over 2. So here, 0 is actually going to be on the top. We're going to have 0 divided by something when I look at the reciprocal. So that's going to give us an answer of 0 for the cotangent function. It's almost like saying the reciprocal of undefined, which is what the asymptote represents, is 0, which is what cotangent shows here. So what happens is your cotangent function on this region here, you can see the tangent values are small. That means the cotangent functions are going to be big. They're going to go up and get close to the asymptote. And then in between, you get a similar type of behavior. It's going to come, and I'm not curving this very well. Let me see if I can do this a little better. So it kind of curves over. Oops, I don't know what happened there. Curves over, and then starts going up rapidly. And then over here, it comes over and then starts decreasing rapidly towards that asymptote. And so we have one cycle of the cotangent function. And one cycle of the cotangent function is much more cohesive than the tangent function. You just get this nice little shape from 0 to pi, whereas up here it's kind of split in half. You get the upward half first, and then the downward half, and it's cut, it's split. But on the cotangent function, you've got the upward half and then the downward half connected with no split in the middle. And of course, if you wanted more periods of the cotangent function, you would do something like this with an asymptote, do it again with an asymptote, etc. Okay? So cotangent is very simple if you understand tangent. Tangent takes some work. Let's make a little summary here. For a complete cycle of the cotangent function or the tangent function, you only rotate through pi radians. This is so important. It's not 2 pi like sine, cosine, secant, and cosecant. And for simplicity, we're going to look at the rotation from 0 to pi. Sometimes you could do from negative pi over 2 to pi over 2 or something like that. And we're going to use from 0 to pi to represent the shapes of tangent and cotangent. And also tangent and cotangent do not have an amplitude or an average value. You could say the average value is 0 if you want, but typically that's not something you look at for tangent because it's not an oscillating function like sine and cosine. All right, so here's our y equals cotangent of x graph, and here is our y equals tangent of x graph, one cycle of each.